I shared a life in the Department of Atmospheric and Oceanic Sciences with Akio for about 25 years. Sort of near early middle of that time, he formally retired, but still came in, and with time slowed down. In generation counting, I am of the successor generation. And though our working styles were very different, I think there are some broad similarities in our paths, and that's part of what I want to talk about today. Within the department, I took over the graduate geophysical fluid dynamics class that he had taught for many years, and my tenure is still running. In terms of real-world global models, he and conspicuously with his University of Tokyo classmate Suki Manabe, really was a pioneer in establishing atmospheric general circulation models that evolved into climate system models. Conspicuously for him, the UCLA AGCM. Later, I took over the global oceanic model component of what was the beginning of the community climate system model system, and we achieved what at the time was a milestone, that is to be able to have coupled equilibrium solutions without serious climate drift in the deep water properties of the ocean, and without using flux corrections, which Manabe was infamous for. And this was essentially accomplished by better parameterizations of the mesoscale eddy effects in the ocean and the surface turbulent boundary layer. Parameterization, of course, was one of Akio's strongest interests. Akio's attention did later shift more to parameterization issues, and as grist for the mill, process models. In particular for him, the turbulent boundary layer clouds, which we hear a great deal about, and the wave drag we heard about yesterday. He was not a direct purveyor of such process model solutions, but certainly paid attention to them, and some of his students we've heard actually used them. When I came to UCLA, I turned away from the global climate problem, anticipating the very slow rate of progress that would ensue, and focused more on local process models. I'll call these in a broad way large eddy simulation models, just as a class of models where you really are trying to be fairly confident of your smallest scale treatments in order to look at intermediate and larger scale aspects of the flow. My own work has focused on, for the ocean, eddies, fronts, wakes, and turbulence in various situations. Climate science is hard science. Its progress is slow. Its essential weakness, besides measurement limitations, is that its outcomes are so strongly dependent on the small-scale processes that I just mentioned that are not fundamentally represented in a fluid dynamical sense in those models. And this is because of the computational compromise that has to be made to make global models. Process models are the bedrock that I'm referring to here, on which to build the foundations of better climate models, at least with respect to their physics. And to the extent that one can obtain for some interesting paradigm flow an essentially reliable solution, because you have confidence that you are not making this resolution compromise on something that's important, then it essentially is certain, and it's as certain as anything can be in climate science, beyond the basic laws. It's not quite at the level of mathematical proof, but on the other hand, fluid dynamicists have never needed to know that the Navier-Stokes might actually have a solution. So, as Akio did, I think, I am pursuing the large eddy simulation path down to the bedrock of reliable representative solutions, which feed into our understanding of how things are working, which leads to conceptual models, which leads to parameterizations. And this is the path I want to talk about here today. Let me illustrate this path by talking about frontal life cycles. Now, with this audience, I don't want to try to force you to be interested in the ocean in its own terms, but I can talk about fronts, and fronts are generic phenomena. Surface fronts are generic phenomena in both the atmosphere and the ocean. And this is a snapshot of a regional model at high resolution of hundreds of meters, nested into a basin scale model that captures the larger scale circulation. And you're looking at the surface vorticity, which is a vertical vorticity, which is a particularly informative field. And if we're going to talk about fronts, the vorticity is a very good indicator of the location of those fronts across the density gradient. And what you see, besides larger scale patterns like the Gulf Streams and mesoscale meanders and eddies, is a lot of fine structure, and that fine structure is what oceanographers have come to call their submesoscale. It's a not entirely geostrophic dynamics, and most of those little stripes and wiggles are strong surface density fronts, and a few cases of, for example, coherent vortices that are spawned by the roll-up of these fronts. If one takes a cross-section through that system, we're somehow overflowing the screen slightly. Never mind. In a east-west cross-section, the vorticity field normalized by the Coriolis frequency is on top, and the vertical velocity field is on the bottom. And in addition to major features like the mesoscale ring, you see a great deal of what in this projection look like very thin structures that penetrate down essentially to the bottom of the turbulent boundary layer, and they have very intense vertical circulations. And so one of the reasons this is considered so interesting is because this really is a principal mechanism of transport of materials and buoyancy from the surface into the more stratified oceanic interior, because these velocities are very large, and they tend to have lifetimes of many hours to days, which are longer than the vertical motions within the boundary layer turbulence itself. And so the goal to find the bedrock is to do a fundamental process study of this phenomena. That requires going down to a large eddy simulation where the turbulence itself is resolved, not just parameterized, the boundary layer turbulence here. And this, of course, leads to big simulations. You have to have resolutions down at meters, and you have to look at submesoscale structure of certainly multiple kilometers. And so I want to talk about just such a problem as an illustration of the approach. Here's a cartoon. It's a cartoon that could have been drawn in an atmospheric conception from Bergeron. It's upside down because we're thinking of the ocean. And the idea is that along the frontal axis, that's a line across which there's a surface density gradient. That surface density gradient penetrates only a modest distance down vertically into the fluid, so it's a near surface density structure. Because of the density gradient, there's at least a partially geostrophic flow along the front. But in addition, in the presence of a larger scale strain flow, a deformation flow indicated by the dashed dot arrows, then that front will sharpen, frontogenesis, and a secondary circulation will be developed in the cross-frontal plane with strong downward vertical motion on the heavy side of the front and upward motion on the light side. And if you look in the Hoskins-Bretherton conception, conservative dynamics, background strain flow, then this will lead to a finite time singularity in the sharpness of the front, as long as it essentially remains two-dimensional as sketched here and balanced. And yet this story is usually told in terms of the effect of strain causing this frontogenesis. That's the initiator. But in fact, this kind of dynamics is a positive feedback self-reinforcing motion in which it's the convergence of the flow at the surface and the secondary circulation that leads to an amplification that is the runaway amplification in this system. Now, let me give several amendments from more the oceanic perspective. Number one, in fact, frontal structures are maybe not even as common as filament structures, that is a two-sided front with a dense core in the center, and then a double secondary circulation is sketched in the upper right. Secondly, the strain-induced frontogenesis is certainly evident, but more often there is a frontogenesis that is generated by the interaction of the boundary layer turbulence. And in a simplified momentum balance, Coriolis force, vertical momentum mixing, pressure gradient in this kind of a density field structure gives you a secondary circulation that is very like the secondary circulation pattern you see with strain, and that is also a very common frontogenetic situation. And then it becomes runaway in the sense that once you start to establish horizontal convergence at the surface, that takes over from the initiated secondary circulation to do the amplification that leads to the finite time singularity, again, as long as it remains 2D imbalanced. So, there is a frontal life cycle that seems to be generic, and it's sort of sketched here. There's initiation with you need a horizontal density gradient, and you can have a larger scale strain, or you can have the vertical momentum mixing. It gets going, and then it keeps going because of the positive feedback with its own secondary circulation convergence. And beyond frontogenesis, which is something that people have looked at a lot, you move into a phase where it becomes unstable. At some point, the instability growth rate of this two-dimensional balanced structure overtakes the frontogenetic rate, even though that rate itself is going to infinity. And then through this instability, you develop frontal fluctuations that cause eddy fluxes that cause an arrest and stop the further sharpening. You're initiating a turbulent cascade down to dissipation and mixing. And eventually, in a steady background environment, the process will peak and begin to decay. At any point, if the conditions favorable to frontogenesis go away, well, then it can sort of lapse into a geostrophic flow along the density lines. So let's do a case study of what is arguably the sort of simplest situation that embodies these ingredients, which is, let's just take the configuration of a filament rather than a front, a two-sided front, and let's make the turbulence by convection, and let's do a really big large eddy simulation. the problem is initiated by essentially a buoyancy restoring under convection in order to establish a density structure on some broader width of the front. And then that restoring is turned off, and so you have the free evolution of a front in equilibrium with its own turbulence. And the generation mechanism is this turbulent thermal wind. There's no external strain. And we're going to focus on the Y average structure, which we'll call the front, and the secondary circulation, which is the Y average structure of the cross-frontal flow, and then the frontal turbulence. In this problem, there are two important control parameters. How strong is the turbulence maintained by the surface convective forcing, and how strong is the initial front measured by the initial density gradient. This problem has complications when you add wind and surface gravity waves, because those add direction to the problem. And so in addition to their magnitude, you have to talk about orientation. But leaving them out for the moment, let's just talk about how this flow evolves. And here are before and after pictures. Before to the left, after to the right, or not after, but at the time of peak arrest. The buoyancy field, seeing the dense filament structure that then sharpens down from several kilometers to about 100 meters width. The along front flow, which geostrophically is a pair of opposing jets in this filament configuration, and it too sharpens down to a very narrow gradient. Do notice that this is a logarithmic scale, so as you can focus both on the larger scale far field and the finer scale near field. And then the bottom two panels are the horizontal and vertical components of the secondary circulation. And they too sharpen down to a small scale, and in particular the vertical downdraft becomes very, very strong. So what does the time series look like for that? Here are two quantities. One is the peak vorticity of the frontal along front flow, and it undergoes a period of amplification and frontogenesis, which, if you want to imagine it, is headed towards infinity. But then it gets arrested, it has a peak value, and it has a longer, slower decay phase. One of the really striking things, though, is how much the turbulence changes in conjunction with the sharpness of the front. That is, the turbulent kinetic energy also enormously amplifies at the same time as the front is sharpening. And that turbulent kinetic energy is being fed by the frontal instability. The sort of initial threshold value is just the effect of the background convection. Arrest happens. In this case, arrest happens because the primary frontal instability is a horizontal shear instability. And so one can look at a balance equation for the frontal along front flow, which is basically a matter of sharpening by the secondary circulation versus turbulent momentum mixing by the fluctuations. And you see here those two terms are, at the time of peak arrest, approximately in good balance, and they have amplitudes that are enormous compared to the convective boundary layer scaling that one would use for such rates. If you look at the kinetic energy at the time of arrest, which is what I'm going to focus on, the kinetic energy, and again this is in this logarithmic cross-front scale, the kinetic energy is extremely intense, concentrated in the core of the filament, and the secondary circulation is of a broader scale, and the amplitudes are essentially comparable. And in fact, if one took out the along front flow component of the kinetic energy, the y average flow, this would even then begin to be a little smaller than that, but of comparable order. One language for talking about how the turbulence is working is the traditional second moment turbulent kinetic energy equation, which rather than writing it out in formulas, I'm just going to give it in words. And so tendencies in the turbulent kinetic energy, which is amplifying in frontogenesis, can be created either by shear production or buoyancy production. It can be advected by the large-scale secondary circulation flow, or it can have its own turbulent transport, or it dissipates. And at, for example, the time of arrest, the turbulent kinetic energy is a maximum, and so there will have to be some sort of balance among the contributing terms on the right side. And so let's first look at some vertical profiles. The one on the left is the far field, and that's just a traditional convective boundary layer. That is, the source of energy is the buoyancy that comes from the surface flux, and the dissipation is the sink, and there's very substantial vertical transport between the strong buoyancy forcing at the surface and the dissipation distributed deeper into the boundary layer. And so it's a non-local balance in a way that certainly the atmospheric communities become very familiar with. Newer, then, is what's happening in the middle of the front, and so here are the same quantities being plotted in the frontal center, and you see it's a very different kind of balance. There's no important buoyancy source. It's all shear production source. That is, it's the shear instability of the frontal flow that is the source of the turbulence. And in fact, its local balance is entirely transport. And so, in fact, it's even more non-local. And look at the magnification by a factor of 1,000 of the amplitudes on the bottom axis. If you look at the pattern in a cross-section, in the time of arrest, back to this logarithmic scale, then you see that, this is part of what gives confidence that we really are resolving the fluid dynamics here. These are all sort of very clean, robust results. That the strong source, this is also a logarithmic scale, centered in the core. There is, of course, a degree of local dissipation. Very weakly, there's a degree of converting of the kinetic energy into buoyancy. That is, it's not like convective-driven turbulence. It's mechanically driven turbulence at that point. But then the transport is this removal from the region of very strong generation in the core of the front, both vertically and horizontally, around to the surroundings, spreading it out. So this is non-local even to a greater degree. So the bedrock that I'm talking about here is trying to figure out what are the important flows, and certainly an isolated, cumulus tower is an important flow, but so is a frontal life cycle an important flow, and doing what it takes to be able to look with confidence at the multi-scale interactions that are involved in this case between boundary layer turbulence and submesoscale frontal structure. In terms of summary, talking about fronts in particular, they are very widespread. They're especially so in the ocean. They have a typical life cycle, which is that frontogenesis is overtaken by frontal instability, which leads to frontal arrest, leads to cascade and dissipation and mixing and then decay, all in a steady environment. Fully developed boundary layer turbulence is an essential component of this life cycle. That is, one really can't stop where Bergeron and Hoskins and Bretherton did by trying to imagine the sort of conservative dynamics of onset under the influence of strain. And the turbulent behaviors are non-local in space is what I showed. They're non-local in time as well, so we're back to the memory effect that people have been also discussing. And so when one comes to the act of parameterization, one really has to have a conceptual model that represents, that is true to these features. In a more general methodological way, I think finding the dynamical bedrock of solutions that you really are confident in for important flows is really our most certain scientific path to making better climate models. Circulation models, that is ones with levels of parameterization, expose the phenomena from the larger scale perspective and the influence down on smaller scales. Large eddy models themselves can yield sufficiently reliable solutions sort of from the small scale building up. And what really has not been talked about in this conference, but has been absolutely central to the methodology that we have been following in the ocean mesoscale and submesoscale, is that if you use grid nesting from larger scale models to set the environment, including its variable form, and you learn how to handle the delicate aspects of open boundary conditions across finer to coarser grid boundaries, building on the fact that essentially almost all small-scale dynamics is locally controlled. But of course, you need to know the environment in which it's being controlled, which means that downscale nesting actually gets you most of the story. And so, better remote observing, David was emphasizing that, bigger computing, everybody emphasizes that, and even machine learning. Is Tapio here? Which I was happy to hear Tapio renounce after certain earlier excess enthusiasms he had, at least got his project funded. They can all help, of course. They're important technology, but it really is the basic fluid understanding that is the bedrock of having proper conceptions of what the small scales are supposed to be doing to help the large scales evolve.
Okay. We have time for some questions.
David.
That was really fascinating, and I sometimes worry that in the atmospheric side we're losing a sense of the importance of fronts as we concentrate more and more on climate and less on other scale. But I had a specific question for you. In atmospheric fronts, you often find in frontal zones manifestations of symmetric instability, which in that case are sort of related to moisture. In the ocean case, I would have guessed that if you had a component of surface stress along the baroclinic shear vector, you'd be having a sink of potential vorticity, you might get the same kind of thing. Is that, you see that? Is that playing any sort of significant role?
You do see it, and Leif Thomas, who is now at Stanford, is a ocean theoretician whose favorite subjects are gravity wave interactions and symmetric instability, has sort of made popular the idea that if you happen to have a front, in particular a more or less east-west front, as happens with the Gulf Stream and the Kuroshio when they separate from the western boundary, and then you have the westerly winds over them, that's a very good generation of negative potential vorticity, and so you can certainly trigger symmetric instability. My view, probably not his view, is that the important thing is to have small-scale turbulence. If it comes from symmetric instability, that's fine. If it comes from convection, that's fine. If it comes from the wind, that's fine. You also can get symmetric instability when you have bottom boundary layer flows with sort of the right orientation relative to whatever density gradient they happen to have. If you look at the statistics of frontal orientation relative to wind direction, for example, they're not strongly peaked at the downfront wind, but it does have its distinctive behavior. I brought this back up just because the way you started it. I did want to ask, but not declare, I don't think the atmospheric community has ever followed through this life cycle in a way that I would call bedrock. I mean, they certainly know about frontogenesis, and there certainly are some examples of front instability, but how does the arrest happen? How does this intensification of the whole turbulent process happen? And, given that one of the references here could be Bergeron 1928, how come you guys have not done your job?
Can I ask another question? I'm a little bit concerned even whether we're doing a good job teaching the dynamics of frontogenesis today in atmospheric sciences. I know it doesn't seem to happen on the atmospheric side of MIT at the moment. I wouldn't want to generalize that. But my other question is maybe a little bit esoteric, but I always considered the Hoskins-Brotherton model to be a really wonderful leap forward in understanding fluid dynamics. And one of the things that was clever about it was to use a kind of somewhat flow-dependent coordinate system. I've always wondered, and this is the esoteric part, do you think there might be still a role for flow-dependent coordinates in more general fluid dynamical problems where you're not making very strong assumptions and idealizations? Or is that just total fantasy?
Well, I think it's hopeful thinking. For this problem, if there's uniform potential vorticity, if there's no variation in the stratification, then those two assumptions, potential vorticity conserved on parcels, geostrophic coordinates to move into, suddenly the solutions are very clear. I mean, that was enormously clever or enormously lucky. I don't think in general we're going to have that luck. The extravagant form of your hopeful thinking is, wouldn't life be simpler in Lagrangian coordinates? The equations are so short in Lagrangian coordinates. The problem is that Lagrangian coordinates do that. And don't get me started on generalized Lagrangian mean theory.
Any other questions?
You talked about the balances of the arrest and the rapid, apparently headed towards finding timing singularity increase in that. But if the arrest was happening on some time scale you could see, you would expect that to curve over gently, but it just stops. Do you have a sense of what sets that arrest? It's so
Well, could I predict this curve from knowledge of Q star and M squared, the two control parameters? No. If you do different values of those, you see these patterns, but the actual amount of amplification and the stretching or compressing of the time scale is the part that I don't have a clear answer for. There is a threshold if you get to really weak initial fronts and strong turbulence, then even though there will remain a memory of the initial frontal pattern, it doesn't amplify. So too much turbulence is diffusive dispersive. But actually, more often, one sees in simulations like the examples I showed that there's a nice amount of turbulence out there that is actually frontogenetic in this turbulent thermal wind. The only qualitative answer I can give to your particular question is that in doing some idealized linear instability problems in Carey's coordinate system, that is following the geostrophic flow compression, the frontogenetic rate is increasing, but the frontal instability rate is increasing faster. And so, if you will, it's a matter of, the frontogenetic curve being overtaken by the frontal instability curve, and, that happens pretty fast. Frontal instability can get, extraordinarily strong in very strong shears. But no, that's not a formula. It's a plot.
Okay, well, let's thank Jim very much.